So, good evening, everyone. So, let us start today's session. Okay. So, can you able to see my screen?
Right now, no.
Yes.
Not yet, ma'am.
Okay. So, just a minute.
Now we are able to.
Okay. Okay. Thank you. Okay. So, yesterday we talked about parallel dot product. We stopped there. What the need for using shared keyword in dot product. Okay, so in this particular kernel code, what we have done is we are performing dot product of A and B, and we are sharing the global memory. So sharing the memory of the threads, then we are storing the results into an array. So after that, we are performing the pairwise products. So for that, thread 0 is used. So in the thread 0, what we have done is we are adding all the dot producted values, that is a naught into b naught, a1 into b1, so that value. So I told there is one problem behind this, that is uh, here all the threads are executed in parallel. So also it is performing pairwise product. Okay, see here. Here one value is there. This we can say these are all threads. All the threads are in consecutive memory location. Okay, so the threads are multiplied and stored there. Okay, so here all the threads are using the same memory or accessing the same memory with the help of shared keyword. Okay, so and summing all the product value in the thread 0. So what happens here is the summing up happens randomly. It won't happen sequentially. Okay, so someone is joined. The previous slide. So what happens is here in thread 0, we are summing all the individual products. That time, the thread 0 can able to access all the remaining threads values in the memory. Okay, thread 0 won't access all the threads values according to their calculation based on the completion of the pairwise product calculation. So it randomly take the values. You can see here. Okay, so it tries to read some thread values before the writing operation happens. Pairwise product writing operation happens. See here, thread 0 finishes is right in step 1. So here, these are all calculated, but so the thread 0 tries to read the value in index 12. Okay, so this is index 12. Index 12 yet to be calculated and stored. What happens is it returns some garbage value. Okay, so we don't get the exact correct value. Okay, so this is a problem while performing um, dot product. Okay, so in previous class one of the students asked like that, so I am, while executing, I am getting some random values, I am not getting sequentially all the values. This is a problem. Threads won't be executed sequentially. It will be executed parallelly. Some threads may executed completed its execution very fast. Some threads it takes some more time. So likewise, it goes on. Okay. So here, what happens is thread 0 is accessing the thread 12 before that particular pairwise product completes. Okay. So this is the main problem. How can we solve this problem? That is the question. So here one more variable we have to use. For that, solving the problem of asynchronous manner of execution of this particular threads. So we have to synchronize all the threads. For synchronizing all the threads, what after synchronization, what happens? So all the threads are once all the completion happens, then the addition process happens. Okay, that is explained here. We are having the shared temp. Then we are using thread idx for pairwise multiplication. We have to synchronize the threads here. Okay, so the reason is no thread can advance until all the threads. So once all the threads completed its execution, so all the threads are having the pairwise product value, then we can perform the summing up all the pairwise products in thread 0. Then so this for that we can use sync threads keyword, which is available in CUDA. Okay, and the main functionality of this is synchronize the threads within the function itself, and the threads in the block wait until all the threads have get the sync threads. Okay, so we can synchronize all the threads within the particular block. Okay. So here in this program, we are using only threads. Okay. If you are using only threads, so we have to mention in a single block many threads. Okay. So that is a concept. So in sync threads can synchronize all the threads within a single block. Okay. If thread 0 is executed, so it is synchronized, and thread 1 it is synchronized, and thread 2 it is synchronized. So all the n threads have been synchronized. Okay. So here the important point we have to remember is threads are only synchronized within the block, within a single block. Okay. So you can rewrite the code with the help of sync threads. Same kernel program, same shared keyword. So after that we are using threads. Then you use sync threads. So after that, there's a summing up code. Okay. So initially the sum value is mentioned as 0. After that, all the threads values have been added with the sum. Okay. So this is a kernel code for dot product. Okay. So now let us see the main function. So the main function, as usual, we are simulating the addition of two numbers, or we are performing dot product of two variables. So here we are using in star A, B, and C. So it is in CPU. The next dev A, dev B, dev C. These are all used in GPU. So next, how to find out the size of whatever maybe it is. How to allocate memory space for all the device variables in GPU. So then for ABC also the memory is allocated in CPU. So then we can use memcopy. So after that, see here the kernel is launched, single block n threads. Okay, if you have written only threads in the kernel, so you have to write only one block. Okay. So then once the calculation completed, you return back the results. So then you are freeing all the memory. So I'll paste the code in chat to try to execute. It's a kernel code. So here in the main program, I didn't assign values to A and B, just assign values to A and B. So I have pasted code. So after allocating memory, just include the code to getting values. So anyone executed? No? I have used I. Okay, so because of copy pasted, there are some. Some int is there. Here, this one. So I don't think whether it's a correct answer or not. So I got some answer. That's all. Okay. So let us see the next one. So this is a review. You can launch the kernels with n threads. That is 1 comma n. So the thread idx.x is used for accessing threads index, and either you can use blocks and threads. That time already we have seen. So you have, instead of using thread idx, you have to use this particular statements. So again in the call, while calling, what you have to do is n slash threads per blocks and threads per comma plus threads per blocks. So have to give. So for in dot product, so we have to use shared keyword for sharing the memory among different threads. And so the main why you are using is, if the threads are running parallel, so those threads are not visible to the other threads or parallel blocks. So next is you have to use sync threads, and for synchronizing all the threads. Okay, so if then only all the threads reach sync threads, then only we can able to add without any data hazards. Okay, next is multi-block dot product. So initially we have seen the single block dot product. Okay, and here we are having only one block and n threads. Okay, and so in multi-block dot product, so the main thing is we are having block 0, block 1, and etc. Okay, in block 0, the dot product happens, and pairwise product. After that, you have to sum up. So in block 1, pairwise product. After that, you have to sum up. So at the end, you have to sum up all the values. Okay, block 0 sum up value, block 1 sum up value has to be added if you are using two blocks. Okay, so that happens here, and then only we will be getting the final result. Okay, in multi-block dot product, of course, we have to use both blocks and threads. And in default case, you have to use the thread idx dot x plus block idx dot x into block dimension. That means how many threads are there in the block. That is block dim dot x. So here in temp, what you have to do is So you have to use this one. So all are taken into a thread ADX. Then next we have to synchronize threads. So after that, so you have to sum up the results based on number of threads per block. Okay. So in each block, how many threads are there? That will be given as there in the condition. Okay, so what happens is next, so in while using multi-block, we'll reach to an race condition. You know what is a race condition? What is a race condition? So what happens while doing race condition? Yeah. So one of you have executed, yeah, we didn't assign values to A and B. So you surely get the garbage value for the previous one. So you have to do all those changes there in the program. So let us see the multi-block. So what happens in the race condition? So here we are using more than one blocks. Okay. So thread 0, block 0, thread 0, block 1. Okay. So the block 1 also having the threads are indexed at thread 0, thread 1, thread 2, thread 3. And block 0 also the threads index are thread 0, thread 1, thread 2, thread 3. Okay. So here also it read the value at addresses and add sum to the value, write the result to the address in the same address, not the some other address. So in the thread 0 also what happens is it read the value at the address, add sum to the value and the writes the result to the same address. Okay. So what happens is here the race condition occurs. Okay. And two or more sequences happening at the same time, race condition occurs. So because of summing up the pairwise products. Okay. So that is explained here. You are doing three operations: read, modify, and write. First we are reading and we are summing. Next we are writing. Okay. So that is explained here. Because of race condition, there is some error occurs. I'll explain here in block 0. So what happens? Thread 0 reads. Okay. So here sum is having the value 3. Okay. The sum variable sum which is having the value, it can assume as it is having the value 3. So initially it reads. Okay. So the value is assumed as 0. Okay. So then it computes. Already sum is having value 3. 0 plus 3, 3. Then it writes. Okay. So while writing, so again the 3 will be returned onto the same address. Okay. So next come to the block 1. Okay. So here block 1, the sum value is considered as 4. Okay. So already we are having the value 3 in the address. Okay. It is read. After that, the 3 has to be added with 4. Okay. So then we'll be getting 7. So after that, the 7 is written onto the same address. This has to be happen because we are using thread 0 for all the addition or summing up all the pairwise products. Okay. So if it happens in this way, there is no problem. Okay. So I come to this okay, particular example scenario. So block 0, it reads 0. At the same time, block 1 also reads. What happens? It reads 0. Okay. So once it's read, it computes. Already the sum value is 3. So 0 plus 3 equal to 3. Okay. So, but here in block 1, it is there in 0. Okay. So in block 1, what happened? The sum value 4 is added with 0. Then it is having the value 4. Okay. So here it writes after block 1 calculation, block 0 return the value 3 to the address. Okay. Before writing 3, block 1 calculated the value. Okay. So in thread 0, what happens? I will coming here. The block 1 is block 1 thread is having the overwritten value of 4. The 4 will be written. Okay. So we won't get the correct answer. Okay. So this is a problem happens while doing multiple blocks. Okay. So while performing multiple blocks, what you have to do is you have to go with some atomic operations or atomic functions. Okay. So yesterday one person has asked about atomic art. Okay. So here while using atomic, what happens is atomic function, the read, modify, and write operations have been done uninterruptible. Okay. So, and a predictable result when simultaneous access to the memory required, we need to atomically add sum to C in our multi-block dot product. So instead of using the previous method, here what you have to do is you have to use atomic add. Okay, there are some different functions are there in atomic operations: atomic add, atomic sub, atomic min, atomic max, atomic inc, that is increment, atomic dec, atomic exch, atomic cas, that is compare and swap. Okay, these are all the some of the functions. I have taken all those functions from this particular document from NVIDIA. So what happens is while using atomic operations, so what it will do is um, it reads the word, either that is reads the data from the memory. Okay, so in some address, either in global or shared memory. Okay, whether the data is there in global memory or the shared memory, that will be read by the atomic add function. Okay, after that, what it will do is it adds a number to that old value, and the result will be written back to the same address. Okay, that happens with the help of atomic add. So if you have used atomic add function, there is no need of using other for loop and all. You can see it here. Okay. So the previous one, what we have done is here also we are having some for loop for adding the value from value sum to some variable c. Okay, instead of using that, you can use atomic add. What it will do is it will take the old value of sum, so and calculate the and find out the new value, then add it to there and uh, save it to the same address. Then only it move to take the value from the next location. Okay, so it happens in the all the memory locations. Okay, so atomic sub, instead of adding and you are subtracting old value my old minus your new value. Okay, then it will be stored in the same location. Okay, so reading, uh, adding or subtracting and storing, all the three operation can done with the help of same function. Okay, so that is atomic add, adds, reads, adds and store. Atomic sub, read, subtract and store. Okay, so atomic min, so the old value and the new value that will be compared and the min value will be stored. Okay, and atomic max is for finding the maximum. So here it is adding 32-bit word. Okay, so in the latest machines you can use 64-bit word and atomic inc. So we can perform some conditions. Okay, there and store the result back to the memory at the same address. These three operations are performed in one atomic operation. The function returns old value. Atomic decrement. This is increment, this is decrement. Okay. So and old minus one, here old plus one. So if old value is greater than old value is greater than or equal to the new value, so then 0, else old plus 1. Okay. So you know that the particular statement in from C. So here the decrement operation. And so here atomic EXEH, it reads 32-bit or 64-bit word. So all the remaining uh, atomic decrement, increment, add, sub, so all those things read only 32-bit. So EXEH, it will read either 32-bit or 64-bit. Okay. And compare and swap. So whether the data is 16-bit or 32-bit or 64-bit. Okay. So anything can be read and the swapping operation performed. Okay, so this is a multi-block dot product. So in this multi-block dot product, already I told. So instead of using simply summing up the values, you use atomic add. So it solves the problem of racing. So again, same thing. So you are using ABC. Okay. So I didn't get the input here. So you have to get the input. So before copy input to the device. So then here in this case, we are using both threads and blocks. Okay. Surely we have to use n/threads per block, comma, threads per block for launching the kernel. After that, you have to get the results to CPU. Then you free the memory, everything. It is not copied. So this is a kernel function. So this code is previously available with you. The same code. You can use that code instead of using this. If you have used this, you have to do some corrections. So you have to get the values or assign some values and all. Having the previous program, you simply take that program and execute. So I have given the program for both the thread and block usage. Not this one. Okay, this one. I'm copying this program. We'll try. Here also, the previous one, I'm getting some garbage value. Okay. After that, you have to copy this code. Is it here? So you have to change the kernel program. One, two, one closed brace is missing. Try to execute, whether it is executing or not, don't know. Multi-block. Again, some problem. Here it is in die. Threads per block is undefined. We will copy paste these things and use it here. Oh my god. Here it is dot. So we have to change here. Okay. Okay, some 14. N divided. What is the value of n? N divided by this one. And so you are having more than one block. Okay. So in one block, 2 into 2, 4. How it is calculated, I don't know exactly. But I got some result. Okay, so I check the results with the actual value and I will tell tomorrow. So what the results you could get. So I'll post all these programs in your sheet. Then you can able to get the sheet. Okay. Okay, so for multi-block, what you have to do is you have to perform atomic. So there is no need for using header file for atomic add. Okay, so it's inside the CUDA. There is no need for that. I didn't include anything. So just include for writing programs in Colab, just include stdio.h for our printf and scanf statements. Nothing else is needed. CUDA.h also won't be needed. Okay. So if you have written the code in some notebook and saving it as filename.cu, then running on command line, that time you have to include CUDA.h and all. Okay. So here nothing is needed. Okay. So for multi-block, we have to use array for avoiding race conditions. So we have to use atomic operations. So there are some atomic bitwise operators operator functions also available for XOR or okay, everything is available. So I have shared that link there. Okay, if you have needed, you can go through that. Okay. So next is one small concept. So we can also execute consecutively threads in single instruction, multiple data. So normally this is called what threads. Currently 32 threads can be used for that. Okay. So if you have using single instruction for multiple data. Okay. So simultaneously or 32 threads can execute multiple data. So usually the warp threads are fully synchronized. Okay. And for after we need some implicit barrier after each step or instruction. So memory coalescing is also closely related to verbs. So what is memory coalescing is if some parallel threads are executing at the same time, some free memory is available. So it combine those free memories and use it for storing and retrieving purpose. That is called memory coalescing. So it is an important one there in the GPU. Okay, so here what we could do is we can uh, use with some conditions, or threads have been used with some conditions. So if some threads are, you can see here, there are some threads from 0 to 7 are there, 8 threads are there. So S0 is executed in all the threads. Okay. So in thread 0, it is idle. No operation is performed. At the time, thread 1 execute S1, and thread 2 is idle, and thread 3 is also executing S1. Likewise, it goes on. Okay. So what happens here is all the threads are not simultaneously executing. So here S2 is executed by thread 0. That time thread 1 is idle. So 2 is executing, 3 is idle, likewise it goes on. But S3 is executed by all the, that is the statement 3, all the threads. Okay. So likewise we can give, and so when different var threads execute different instruction, threads are set to diverge. Okay. So we can say the different threads are not executing same instruction. Okay. So otherwise we can say var threads execute different instructions. Okay. That situation is called as diverge. Okay. This particular situation. Okay. While executing S1 in thread 1, 0 is idle. Okay. This type of situation is called as diverge. Okay. Okay, so what happens is the GPU hardware executes the threads while satisfying some conditions. So sometimes other threads execute a no operation. That means it is idle. Okay. So what happens is why we are saying is it is diverges. While performing this one, uh, some sequentiality is uh, encourages there in the execution. Okay, so the sequentiality addition is called as thread divergence. Okay, so what happens is S0, then thread 1 execute S1, after that thread 0 execute S2. Okay, some sequential execution happens there. Okay, so it won't be actually what parallelism is, all the statement have been should be executed by all the threads simultaneously with different data. Okay, so that is the parallel, because GPUs are meant for data parallelism. Okay, if it is not happening, we can say some sequentiality is there, so it is called thread divergence. Okay, so what happens is uh, why this happened is because of some conditions we have given in the program. Okay, here what is given is if vector size less than n, you execute S1, else execute S2. Okay, so vector size is less than the our defined value of n, we are executing S1, otherwise S2. In some cases S1 will be executed, in some case S2 will be executed. Okay, so all the threads are not executing the same statement. Okay, so again another one condition is given. If id divided by 32 is true, S1 will be executed, else S2 will be executed. So these type of statements makes thread divergence. Okay, that means some sequentiality is included there. Okay. So again, one more. What we have to do is to remove the thread divergence. We have to minimize the conditions. Okay. So if more conditions are there, so you use some sort of threads and blocks to reduce the thread divergence. And while performing GPU programming for large, huge amount of data. So of course we have to use both block IDX and thread IDX. Okay. So here in this program, what happens is they have used block IDX and thread IDX. So there are some uh, what is called this is used here. So vector is used here where block size is given as 1024. So the default number for block size is 1024. That is used here. So here are some main functions, some values. Here two inputs, that is command line inputs. Okay. So for that also we have to use declare the variable for GPU, and you have to allocate the memory space and everything. So here we are launching the kernel with the help of n blocks, comma block size. Okay. So here both threads and blocks need. If you want to use both threads and blocks, what you have to do is the n has to be divided by block size. Okay. So here what is calculated is some strings have been used. So string length something else is calculated, and n divided by block size is calculated, and it is there in the number of blocks. So number of blocks, comma, the block size is given. Okay. So the value is vector. Vector is passed here because the kernel we are having one argument vector that has to be passed. So this is a simple simulation program. If you want, you can execute. And here there are some problems are there. You won't directly write uh, vector id equal to id. So you have to check some condition here. So otherwise it will access out of bounds. So and also in seal we have to convert it into floating point operation. Okay. See here, if id less than vectorize, okay, vector id equal to id. Okay, you include one more variable. So what about the size of your vector? Okay, so id has to be increased or incremented up to vector size. Okay, beyond that it won't be incremented. So in the previous one, you have given the vector. We didn't mention vector size. What happens? So the block IDX and the thread IDX are incremented automatically. Okay. So up to out of bounds. Okay. So to avoid that, we have to give the vector size, and after that you assign. So here you have to give some float. Okay. So both the things you have to consider while getting large amount of data. Okay. So one more reference is there, CUDA by example. So I referred this textbook and this particular URL. Okay. Okay, in today's class, so we have discussed about what is, how can you include that is synchronization threads while performing dot product. Okay, so after that, we have executed the program for performing dot product using multi blocks. Okay, So how to avoid race condition and all. For avoiding race condition, we have to use the atomic functions. So for addition, we have used the atomic add function. So we have seen the other functions too. So after that, we have seen what is thread divergence, what is what threads, and so what are the things you have to consider uh, while executing large amount of data in GPU. Okay. So, so any doubts? Any other doubts? Okay. So then, in the tomorrow's class, I already told the today's class we can go with grid dimension, but instead of completing dots, that is, we'll see the grid dimension in the next class. Okay. So thank you again. We'll see tomorrow at the same time. Okay. Try to join in the same email ID you got given for registration or you got the invitation. Okay. So somebody is waiting very long time in the lobby. To avoid that, so try to log in using the same ID. Okay. Thank you. Thank you all.